Okay, in this video, we continue our discussion of interval estimation in the Bayesian framework. We are still considering the same reference book, Empirical Bayes Methods, second edition. We consider session 1.5. This session consider Bayes' decision between two composite hypotheses. Okay, let us consider the following setting. We have a partition of the parameter space. Remember, the parameter is denoted by lambda, okay? The parameter space is separated into sets B1 and B2. The first composite hypothesis H1 is that lambda is in B1. The second hypothesis H2 is that lambda is in B2. Okay, then our decision problem is we need to construct a partition of the sample space. We partition the sample space into two sets, A1 and A2, okay? And remember, the random variable or the data that we have is denoted by X, okay? Let's consider the base width here. The base width is denoted by W delta. Delta is our decision. The base width consists of two double integrals. The first integral here represents the cost of making mistake when we accept H1. When do we accept H1? We accept H1 when X is in A1. Okay? And when do we make mistake? We make mistake when lambda is in B2 in fact. So we mistakenly accept H1. Okay? The inner integrals means the total probability of lambda in B2. So it is an integral of the conditional likelihood over the value of lambda in B2. The integral is with respect to the pi g. Okay, and then we take another integral over the value of x in A1. Okay, so the whole double integral is the cost of making mistake when we accept H1. The interpretation of second term is similar. We accept H2 because X is in A2, okay? And when do we make mistake? We make mistake when, in fact, lambda is in B1, okay? So first, the inner integral, we take integration over lambda in B1, and we add up all the conditional likelihood with the weighting determined by the pi, and also the second integral is over the value of x in A2. So the altogether this thing represents the cost of making mistake when we accept H2. Then let's try to see how to construct the set A1 and A2. The logic is very similar in the case where we consider simple hypothesis. For a particular value of x, we think about the following problem. If I put x in A1, what is the cost of making mistake? The cost of making mistake is we summing the conditional likelihood when in fact lambda is in B2. Okay, so we take integral with respect to the pi when the lambda is in B2. Then also we think about if we put x in A2, what is the cost of making mistake? The cost of making mistake is we integrate the conditional likelihood weighted by the pi, and we integrate it over the value of lambda when lambda is in the set B1. Okay, then these are the causes of making mistakes. So when the cost of putting in A1 is lower, then we put it in A1, right? So that's why we have the following conclusion, very straightforward. In the left-hand side of the inequality, when the cost of putting x in A2 is larger than the cost of putting x in A1, then we should put x in A1. Okay. Then we transform everything in terms of posterior probability as usual. Now pay attention to the orange color. We derive both sides of the inequality by the marginal density or probability fx. Then the interpretation is as follows. The left-hand side become the posterior probability of lambda in B1 conditional on x. The right-hand side become the posterior probability of lambda in B2 conditional on x. Okay, so whenever the posterior probability of lambda in B1 is larger, then we should put x in A1. Okay, and similarly, when the posterior probability of lambda in B2 is larger, we should put x in A2. So very straightforward. Very similar to the argument in simple hypothesis. The only difference is that the cost here have an integral, but in the simple hypothesis, we don't have the integral. Okay, so very straightforward. Then let's consider a special case application essentially. The application is the situation where lambda is a location parameter. What is location parameter? The location parameter separate the whole real line into two intervals. Okay, so the hypotheses are as follows. H1 is lambda smaller than lambda 0. H2 is the situation where lambda larger than or equal to lambda 0. The cutoff point is lambda 0. Okay. Then it is very straightforward that we make use of the result that we have. Okay. Whenever, let's pay attention to the blue color first. We put x in A1. Whenever we integrate the conditional likelihood function, over which interval? Over the interval from negative infinity to lambda 0 is larger than we integrate the likelihood from lambda 0 to positive infinity, weighted by the pi, surely, right? So a straightforward conclusion from the previous page. And then now pay attention to the orange color. I derive both sides of the inequality by the marginal density, and then the whole things become the total posterior probability in the interval. Okay, so in this simple situation where we have only two composite hypotheses, we could have an interpretation to our result. So what is the interpretation? Because for example, in left-hand side, this integral represents the total posterior probability from negative infinity to lambda 0, right? And the right-hand side is the total probability from lambda 0 to positive infinity. So it is somewhat related to the position of posterior median of lambda, okay? And in this simple situation with only two composite hypotheses, it is straightforward to conclude that we accept H1 if the posterior median of lambda is smaller than the cutoff point lambda 0, and we accept H2 otherwise. Okay.